So the next thing we're going to look at is percent yield. And this is a little easier calculation than the other things that we've done, but it still depends on the other things that we've done as well. Now, the percent yield, when I say yield, it must be a product, and that is key. So you can't talk about percent yield and look at an amount of a reactant. You've got to work through and get an amount of your product. And there's a simple little calculation for this. Percent yield is the actual yield divided by the theoretical yield times 100. Now, you may not really get what these two are, so that's one thing we need to talk about. But they're kind of what they sound like. So the actual yield is the amount that you actually get from a reaction. So it's the amount of a substance produced from the reaction, and it's measured after the reaction is completed. So if you were in the lab, you could figure out your actual yield. You could weigh it on the balance, find out how much you got, or find the volume of gas. Find some way to measure what actually was produced from this reaction, actual yield. The theoretical yield is what you've been doing in every BCA chart that you've looked at where you've looked at a yield. It's the maximum amount that can be produced from that reaction. So based on the reactants you're given, there is some theoretical maximum that you can get if you use up all of the reactions. It's calculated from your BCA chart. It's just what you get from your stoichiometry problem. And if you read the little intro on Canvas, you saw where I talked a little bit about the fact that actual yields and theoretical yields usually aren't the same. The actual yield is most often less than your theoretical. There might be side reactions that happen that use up some of your product. There might be product lost in the process of the reaction. There might be an equilibrium, which we're going to talk a whole lot more about if you're taking AP Chemistry. But sometimes reactions just hit one point where a certain amount of product is produced, and then they sort of kind of go back and forth between products and reactants. So lots of reasons actual yield may not equal theoretical yield. So if you're right now at this point just looking at problems, how do you know that you've got a percent yield problem? So the difference between these and everything else you've done is you're going to have an amount of product given. You're going to have an actual yield given to you. You have to be told. And usually, of course, this goes along with the reactant amount that you start with. So like the limiting and excess reactant problems, you're probably going to see two amounts in the problem. In this case, one of them is probably going to be a reactant, and the other is going to be one of your product amounts. So as with many, many things, I keep telling you, the easiest way for me to teach you about this is just to show you a few problems and how this works. So I've got several practice problems, but if you get this, you can stop this video and just move on to the practice problems that are there on your Canvas page. So chlorobenzene is C6H5Cl, and it's used in many important chemical processes. It's a precursor to a lot of different chemicals. And the chlorobenzene itself is produced by reacting benzene, which is C6H6, with chlorine gas. So chlorobenzene, you get it. Alrighty. So this reaction looks just like this. C6H6 plus Cl2 is going to give you the chlorobenzene plus HCl. And it looks like maybe I didn't balance this. There aren't any coefficients there, but if you look really closely, it is balanced with everything in a 1 to 1 to 1 to 1 ratio. So I went ahead and drew our BCA chart, and then here's the question. When 36.8 grams of benzene reacts with excess chlorine gas, so they already told me that this is going to be my excess reactant. What is the percent yield of chlorobenzene? If I got 38.8 grams produced. So I do have two amounts here. One of them is of a reactant, and the other is of the product. So I have to start with my reactant, 36.8 grams of benzene to C6H6. And as you know, rule number one, or maybe it was rule number two, the main rules of BCA charts, moles only. So I've got to convert this to moles. So I have 6 carbons. If I look up carbon on the periodic table, it's 12.01 grams. So 6 of those times 12.01 plus 6 hydrogens, 1.01 each. Again, hopefully we know that one by now. 78.12 is my mass of benzene for 1 mole. So 36.8 divided by 78.12 to 3 sig figs is 0.471 moles. And so now I'm ready to start my BCA chart. 0.471 moles. So everything is 1 to 1. I start with no product. So minus, plus, plus. And by this point, you probably don't need to go through all of the BCA chart, but I'll go ahead and fill it in for you. You can just get the information that you need. You don't always have to show this whole process. So I know that I should get 0.471 moles of chlorobenzene. But I have a mass here to compare it to. So I could convert this to moles, but I'm just sort of in the compare moles, I'm just sort of in the habit of using mass all the time. So I'm going to take this amount of moles. But now I'm talking about the chlorobenzene. So C6H5Cl. So I'm going to convert this to a mass so I can work with this mass here. So 0.471 moles, and I've got to add these up. So I've got 6 carbons. I have 5 hydrogens now. And chlorine is 35.45 grams per mole. So 112.56 grams. So 1 mole is 112.56 grams. So I'm going to multiply that by the number of moles. And that's 53.015, 3 sig figs there, so 53.0 grams that I should have gotten from this reaction. Now, this is my theoretical yield. Theoretically, that's what should have been produced. But actually, only 38.8 grams were produced. So, out of room here, I'm just going to slide another piece of paper here under it. Sorry. So, my formula for this, like we said on that first page, actual yield divided by theoretical yield times 100, because this is my maximum. The part divided by the whole amount I could have gotten times 100 gives me a percentage. So plugging this in, actual yield from the problem, 38.8 grams, divided by the theoretical yield that I should have gotten, times 100. 73.21, actually just 3 sig figs, 73.2%. So instead of getting 100% of what I thought I should get, I got 73.2%. So that's really all there is to percent yield. Not too bad. Let's look at one more, or maybe 2 more. So here's one. Carbon disulfide burns in air to produce carbon dioxide and sulfur dioxide. So on this one, they weren't as nice as they were on the last one. They didn't give me a equation. but that's all right. I know how to do this. Carbon disulfide, CS2, burns in air to produce carbon dioxide. So if it's burning, that's combustion. I'm adding oxygen. I get CO2, and sulfur dioxide would be SO2. So step one is write the balance equation. We've got an equation. It is not balanced yet, so look at my carbons, they're balanced, but my sulfurs aren't. So 2 there, I need 2 there. Then I'm going to come back and deal with oxygen. I have 2 on the reactant side. I have 2 plus 4, 6 on the product side. And coefficient of 3 there gives me 6 in the reactants. So, got my balanced equation. What is the percent yield if the reaction of 42 grams of carbon disulfide produces 61.4 grams of sulfur dioxide? So there's my information. On this one, I'm just going to fill in the information that I need. We're assuming this is excess, so I'm not worried about it. I'm going to have to convert 42 grams of my carbon disulfide to moles. So for the carbon, its mass is 12.01, and for 2 sulfur, it's 2 times 32.07 grams per mole, 76.24. So 42 divided by 76.24 is 0.551. So if I react all of that, those are moles. I'm just interested in my sulfur dioxide, so that's all I'm going to do. This is a 1 to 2 ratio, so divide that by 1, multiply that amount of moles by 2, I get 1.10. And so this is the number of moles I had. Now I'm not quite there yet. I need a percent yield. So I'm going to take that 1.10 moles. This is sulfur dioxide. So sulfur we said was 32.07. 2 oxygens are 16 each, so 32 total. 64.07 is the mass of 1 mole. Times 1.1 is 70.48. So 70.5 grams. So theoretically, I should have gotten 70.5 grams. In reality, I actually got 61.4. So actual over theoretical times 100 makes it into a percentage. Got my sig figs there. Then times 100, 87.09. So 87.1% is my yield. And so again, that tells you a little about the efficiency of the reaction. It's not 100% efficient. I got 87.1% of what I should have. So guys, that's a couple of percent yield problems. I'm going to post one more short video where we look at what to do if maybe they give you the percent yield and you have to work in the other direction. You could probably figure it out, but I'll put that example up there. So if you feel like you're ready to start the practice problems, then that's fine. If not, there's one more video to go.